So we were talking about doing better in terms of order of the approximation. كان عنا order H explicit implicit approximation, and we wanted to go further, يعني to make an approximation that gives a better order. That's why we proposed the Richardson extrapolation. I'll detail the idea on the right side. So let's say we know that every function which is C infinity, so we don't have to bother ourselves with the regularity of the function. If it's C infinity, so we can write a Taylor expansion of this function to a very high order as much as you want. So if we take the Taylor expansion written in here, so written in here, this Taylor expansion is the formula that we all know. From this Taylor expansion, we can conclude that f prime of x can be written as f of x plus h minus f of x over h minus h over factorial 2 f double prime of x minus h2 over factorial 3 f triple prime of x minus etc. Okay, so we have this form, and in this form the term f of x plus h minus f of x over h, it's, and listen exactly to what I'm saying, it's the explicit approximation of the derivative of f at the point x with a step size equals to h. يعني h is equal to xi plus 1 minus xi, و f of x plus h minus f of x هي yi plus 1 minus yi. Okay, so we can read this expression as follows: f prime is equal to this approximation plus this error term. Okay, so this is the error term, which is led by the term in h. يعني the lowest degree of h in this term is 1. This is the leading term. So if h is small, all the terms h squared, h3, etc. are very small with respect to h. So this is the leading term. And this is the term that will give the idea of the order of the error. So the error here is of order 1. What I will do is the following. First, the approximation in here, I will denote it, we already denoted delta h f over h. هلا I will denote it phi h of f. So what is phi h of f? It's the explicit approximation of f prime at a point x, if it's phi h of f of x. Okay, let me remove this equal in here. So it's f of x, voila. Okay, so it's the explicit approximation of f prime at x. What I will do is the following. I will take this form I already wrote. I will write it again. F prime of x equals f of x plus h minus f of x over h minus h over factorial to f double prime of x minus h squared over factorial 3h triple prime of x minus etc. And I will write it once more, but this time taking 2h as a step size instead of h. يعني we will write again once more. If we write again once more the Taylor expansion, but taking 2h as a step instead of h, so the Taylor expansion will read f of x plus 2h equals f of x plus 2h f prime plus 2h squared over factorial 2 f double prime, etc. And from this expression, I will conclude the f prime again. So it will be like this. It will be f prime of x equals f of x plus 2h minus f of x For those who will not understand from where I am getting this expression, so I repeat, they should write the Taylor expansion with 2h instead of h, and then they will conclude this formula. Minus h 4h over 2 factorial 2 times 2 f double prime of x, and this is because instead of h we have 2h, so in the Taylor expansion it will be 2h squared, yani 4h squared over factorial 2, and there's another 2 that will come from the fact that the coefficient in front of f prime, which is 2h, will divide by it the whole expression. So we have a 2 that will come in here, minus it will be 8h squared over factorial 3 times 2 f triple prime of x plus etc. Okay, so minus etc. It continues. Then once we have these two expressions, look what I will be doing. I will take it as two equations. I will multiply the first one by 4, and I will subtract it from the second one. Why is that? Because if I do so, if I multiply the first one by 4, this is a multiply in here. Okay, it's not a x. If we multiply the first one by 4, in the first term of the error term, yani the h over 2 f double prime, we will have 4h over factorial 2 f double prime. It's minus 4h. Then if we subtract the second equation, it will be minus 4h over 2 f double prime from the first one, minus yani plus 4h over factorial 2 times 2 f double prime. Sorry, I made a little mistake. I will multiply by 2, not by 4. Okay, so if we multiply by 2, so we will have 2h f double prime. So we will have 2, I will write down 2f prime of x minus f prime of x equals to 2. The first one, the f of x plus h minus f of x over h. So this expression, we already denoted it phi. Oh, sorry, the screen has moved, and we'll get it back here. Okay, so the first one, it will be 2. This expression f of x plus h minus f of x over h, we already denoted it phi h of f of x. Okay, minus we take the second expression of the approximation of the derivative, which is down here. So this one, we take this one, so it's phi 2h, because it's the explicit approximation with a step size of 2h of f of x. Okay, then the second term, which is surrounded in green in here, will vanish, because we'll have h f double prime minus h f double prime from this first equation, and then plus h f double prime from the second one. It will vanish. And this is the interest of the method. This is why I multiplied by 2 and then I subtracted. Why? Because if I do so, I will lose the term in h, and the leading term in the error expression will be h squared. Yani the order of the error now it's 2, because it starts by h squared and all the other terms are of higher orders. So I will have here minus h squared times something, I don't care what is it. It's h squared times something independent of h. Okay, so all this is independent of h. Yani, look how I'm gonna read this equation. This is f prime in here, the exact f prime. It's equal to 2 phi h f of x minus phi 2h f of x plus an error term of order of h squared. So if I consider this green expression, this expression in green in here, as being the approximation of the derivative, this will be an approximation with an order of h squared. Yani if you want to have an approximation with an order h squared, all you have to do is to calculate phi h, which is the explicit approximation with a step size h, and then phi 2h, which is the explicit approximation with a step size 2h, and then the first one times 2 minus the second one, and then you will have an approximation with an order h squared. Yani if you divide h by 2 to improve your approximation, your error will be divided by 4. This is why what I explained when I was talking about the orders, about the order of the error. Okay, so we go back to the written text. This is exactly what's written in here on the left side. So if we write f prime and f double prime as I said, okay, and then we multiply the first one by 2 and then we subtract them, we will have an order of h squared somewhere in here. Okay, so phi 1h, now it will be denoted phi 1h. It's this approximation 2 phi h minus phi 2h, and this is what I call the explicit Richardson extrapolation operator of first order. Okay, explicit because I'm using explicit approximations. First order because it's when I calculated two explicit approximations, I calculated the extrapolation. It's a first order. That's I will call it a first order approximation. Then when I will use two Richardson extrapolations of first order to obtain a new approximation of third order, it will be the second order. I repeat. So now we are glad that we have an approximation of second order. This is very good. We want to do even better. To do better, I will do the same procedure, but instead of doing this procedure for phi h, I will do it for phi 1h. Yani, this is what I will do. If we move here, we will see that we know that the f prime can be written as the phi 1 of x plus an error term, oops, sorry, back to the screen. So with an error term of the order h squared and higher. Okay, so if we do so, we can calculate f prime with the first order extrapolation, and then another f prime with a first order extrapolation, but instead of h we have 2h. What does this mean? Follow me well. When we calculated phi 1h, we said it's equal to phi 2 phi h of f of x. Okay, I'm reducing a little bit the notations, minus phi of 2h of f. Okay, هلا if you want to calculate phi 2h, we will use sorry, the screen is bugging here. Let me do it again. So if we write phi 1h as 2 phi h f minus phi 2h, I will calculate another phi 1h. I will calculate another phi 1, but using 2h, and it will be 2 phi 2h of f minus phi 4h of f. So if we calculate these two expressions, yani phi 1h or phi 2h, using for the first one explicit approximations for h and for 2h, okay, and then the second one two explicit approximations for 2h and for 4h, for phi 4h, then we will be able to calculate the follows. So we go back. If we have f prime with an order of h squared, and then f prime, the second one, with an order of h squared as well, then we will be able to combine these two. I will remove these circles that are hiding everything. So this is the order 2 in the first expression, and this is the order 2 in the second expression. If we have these two expressions, I will be able to combine both in order to remove this second order and obtain a higher order. يعني, again, we calculate phi 1h and then phi 1 2h. We write these two expressions, and then if we multiply the first one by 4 and we subtract the second one, this one times 4, and then we subtract the second one, we will obtain the following: f prime is equal to 4 phi 1h minus phi 1 2h over 3, plus something with the order h3. Lekin we were able to obtain an approximation of the derivative with a higher order, which is h3. So all we have to do is to calculate phi 1h. To have it, we have to calculate phi h, phi 2h, and then phi 1 2h. To have it, we have to calculate phi 2h and phi 4h, and then we combine both. We obtain an approximation with a higher order, which is h3, and so on. We can go further. We can calculate higher order extrapolation operators as much as you want. Okay, of course, if we want to calculate more, we need more data points of the function. I will make an example so everything will be clear, but let me point out that you should understand very well the procedure we use to obtain this result, because sometimes in exams we might ask about the procedure and not only the formulas. So this is the general form of the extrapolation operator that you should know. Okay, you should memorize this form so you can apply it for the zero order, the one order, the second order, etc. The zero, when I say the zero order, I mean phi h, which is exactly the implicit approximation of the derivative. I will take as an example. I will take the table that we had earlier. Let me write it down here. It's better now. So to make it easier for you, look how are we going to proceed. So here on the right, you see I have put the table that you have in the beginning of the chapter. This is the function j, okay, that we wanted to use in many examples. So if we take this function and you want to calculate the approximations of the derivative at the point 0 using the Richardson extrapolation operator. So I will show you how to proceed. Look what you will do. To make it easier, to make the calculation easier, we'll use this algorithm or this technique. We will make a table that contains h, which are the step sizes, okay. So if we are at the point 0 now, we will use many step sizes like 0.25, and I will use 0.5 and 1, and now I will keep the first row empty. So 0.25 and 0.5 and 1, we can notice that from here to here we are multiplying by 2, and from here to here we are multiplying by 2, because when we use Richardson extrapolation operators, you can remark that we are using always the approximation with a step size and then the approximation with the double step size, phi h, phi 2h, or phi 2h, phi 4h. That's why we use step sizes which each one is the double of the one before. Then in the first column after the step size, we have the phi h, which is the delta h of f over h, the explicit approximation, of course at the point 0. Okay, so to calculate this, we have to calculate yi plus 1 minus yi over 2. So in the first case in here, to calculate this number, this is the approximation, the explicit approximation using a step size of 0.25. So if we go back to the table in here, it means that it's yi plus 1 minus yi over xi plus 1 minus xi, and this will give a number like minus 0.0622, etc. Okay, to calculate the number in this case, so it's the explicit approximation with a step size of 0.5 at the point 0. So it will be, again, back to the table, it will be this number yi plus 1 minus this number yi over xi plus 1 minus xi, and it will give a number like minus 0.12306, etc. Okay, again, to calculate the number in here, it will be, it's the approximation of the derivative at 0 with a step size of 1. Step size of that 1, it means that it's this number in here minus the first one over 1 minus 0, and to give a number like minus 0.234802, etc. Okay, now the second column will be dedicated to the first order extrapolation operator at f of 0. How to calculate this? From the formula we have, phi h1, it's equal to 2 phi h minus phi 2h. So to calculate the number in this case in here, and this at this place, it's 2 times what's in here minus what's in here, because with respect to here, يعني what we have in here, it's the phi 1, be careful, it's 0.25. Okay, so the phi 1 0.25, it's back here, it's 2 times phi 0.25 minus phi 0.5. So it's 2 times minus 0.0622 minus 0.12306, and it will give a number like minus 0.00145, etc. Okay, then what's in here, I will make it a bit long to write it down. So it's the phi 1 0.5, which is 2 times phi 0.5 minus phi 0.5 times 2, yani phi 1. So it will be 2 times minus 0.12306 minus 0.234802, and it will give minus 0.01131, etc. Okay, now in this case, in this place in here, we cannot calculate phi 1, because to calculate phi 1 in here, it's phi 1 1. We need phi 1 and phi 2, and we don't have a phi 2. That's why I kept this place empty. So if we want to add 2, then we can make the calculation of phi 2 in here, and then from this we can conclude what's in here. We're not gonna do it, but we can do it if you want. Okay, now the third place here will be dedicated, the third column, I would say, it will be the phi second order hf0. So in this first place in here, it's the phi 2 0.5. Phi 2 0.5 from the formula phi 2 0.5, sorry, it's a big phi always. It's 4 phi 1 0.5 minus phi 1 1 over 3. Okay, sorry, I made a mistake. It's 0.25 in here. Down here, it's 0.25. So in here, it's 25, 25, and 0.5. Okay, so it's 4 times what's in here minus what's in here over 3, and it will give 0.00183, etc. And to calculate the phi to 0.5, we will need the phi 1, which should be in here, but we don't have it, so we can't do it. So our table will be empty in here, put x's, empty in here, and everywhere else it will be full of numbers. So this is the second order approximation with the second order Richardson extrapolation. Okay, so this table you have it properly written on the second page in here. So it's properly written in here. I will let you with the remaining part of the Richardson extrapolation of the first order derivative, because because it's the same thing. You can make the implicit extrapolation operator with the same procedure, and you will have this kind of expression, which is very similar to the explicit one. And you can make also a Richardson extrapolation operator for the centered approximation. Oh, sorry. So for the centered approximation, it's the same procedure. I will let you read it alone. So it's the same procedure, but it will give higher orders, as you may see in here, because originally from the starting point, the centered approximations has a higher order than the explicit and the implicit one. And be careful that the with the centered approximation, the expression is a bit different, because here you have 2 to the power 4 and not 2. You don't start with 2. So we can write it as in the general form as in here, and this is what you should know. This is the Richardson extrapolation for the centered approximation of the derivative. Okay. So in the next video, we'll be talking about the second derivation, the second derivative, and how we calculate it. Thank you.